which is one of the things that we have to spend our time on, which is why I started the course the way I did the first day with reviewing the concept of protecting groups. When we have a functional group that is reactive, and believe me, carbonyl groups definitely qualify, we sometimes want them to stay out of it, which means protecting groups come up. In terms of the alcohols, there are literally hundreds of them. So specific examples are almost a waste of time. There's too many to be bothered with. There are a few that are common, but conceptually they all work the same. You form an ether of some form temporarily, you break it off later. There are not that many good protecting groups for aldehydes and ketones, so those we have specific examples we need to think about. The most common one is an acetal, and it looks like this. If I take an aldehyde or a ketone, for my purposes, essentially everything that a ketone can do, an aldehyde can do as well. There are rare exceptions, but we're not going to dwell on those. I don't think there are even any of them in your book. If I treat this in the presence of an alcohol, and our friendly neighborhood strong acid again, with the loss of water, I'm going to first go to this, which is called a hemiacetal, and then continue to this, which is the acetal. The acetal is our generic aldehyde and ketone protecting group. It can be removed and return us here with acid and water. Our initial conditions are generally sulfuric acid and the alcohol. We're excluding water largely. And we sometimes will manually remove it by a physical trick called an azeotropic distillation. But we're not going to worry about that for the moment. Okay, so drawing this out is going to take a little time. It's a lengthy mechanism. But the point is, it follows some very, very simple principles over and over and over. There are multiple steps, but they're very predictable. Predictable part one, sulfuric acid protonates any lone pair it can get its hands on, like oxygens. Predictable part two, if you have a carbonyl that's protonated, it's susceptible to weak nucleophilic attack. Predictable part three, if you protonate an alcohol, you've just created water. That's a damn good leaving group. Those are things that happen over and over and over, and they'll all happen in the course of this mechanism. So, let's talk about that. Let's make it a real example for the fun of it. All right, let's make it just benzaldehyde. We'll do it with methanol. Simple, direct, drawable. We could use a lot of different alcohols. We could use a lot of different aldehydes and ketones. It really doesn't matter as long as there's nothing else around that's acid sensitive. This is a strong acid set of conditions. So if we had something that doesn't tolerate acid well, this would be a bad protecting group to use. Unfortunately, you don't have many other options. There aren't many protecting groups that work for aldehydes and ketones that can be taken back off. This is one of the few. So, first step, predictable as I said, protonation of the carbonyl group. Sulfuric acid protonates everything it can get its hands on. At that point, we're susceptible to weak nucleophilic attack, so here it goes. Here's that phrase again. Nucleophile attacks the pi bond, gives me a tetrahedral intermediate stage. All of this, by the way, is reversible. Since we're usually using the alcohol as a solvent, and it's very similar reaction-wise to water, it can do the same acid-base type of chemistry water does, and not require me using something silly like the hydrogen sulfate anion as a base. Okay. So here's my hemiacetal state. I have one alkyl group in place from the alcohol. I still have one OH group. I have not finished the job yet. But I've gotten the halfway point. It's not really the halfway point. The mechanism is more loaded to the second part than the first, because we didn't have to actually get rid of anything yet. Now we got to get rid of the OH, replace it with another O group, so we've got a little bit more of a complicated few steps after this point. So I'm here now, redrawing so we don't lose track of what we're doing. I'm still in a sulfuric acid medium. I could use the protonated alcohol that I used as a base in the other step, or I could draw it using this. It really doesn't matter whether it's equilibrium or not, since it is, the whole thing is reversible equilibrium, but I have to make that oxygen into a leaving group before I can get rid of it. It is not going to leave until I've managed to make it want to leave. Now, let's get this in our brains early. Let's get this in our brains strong. You should have gotten this in part 1 when you did the SN2 reaction. The hydroxide group is an atrocious leaving group. It is not, generally speaking, a reasonable leaving group. One of the most common things that will happen in drawing out a mechanism like this is that people will just make the OH group leave. Let me go back a step. You are in concentrated sulfuric acid. Do you really think the hydroxide ion is going to form under those conditions? Answer, no. Not a chance in hell. So don't draw that. It hurts my head. Strong acid conditions do not generally form OH groups. Okay? Just basic general chem stuff. Let's get that out of the way. Occasionally, I realize that exam day is stressful and you forget some obvious things. Let's not go that far. Okay. Now, we have a water leaving group. We can actually reform a carbonyl in sort of a precursor to what we're going to see a lot of later on in the esters and related chapter. But this is not a carbonyl that's protonated. This is a carbonyl that's alkylated, because we reformed it from the OCH3 group. What if I reform from the OH group? Well, then I'm going backwards. Like I said, this is all reversible. What we're drawing in the forward direction here is the only steps that are productive. Protonation, deprotonation, attack, and displacement are reversible steps all through this. Now, I still have a cationic oxygen, which means it's still susceptible to weak nucleophile attack, so the second one does the job. Now, I have the second one coming in. I displaced water here. I could use that as a base. I could use the alcohol as a base. Doesn't matter. As long as I'm not writing anything silly, either is appropriate. So I deprotonate that. And I'm here, which is my acetal. Now, if I want to use something that was going to be problematic for the carbonyl group, I can, because it's not there anymore. I don't have a double bond to oxygen to worry about breaking with a strong nucleophile anymore. I've gotten rid of it in a way that I can get it back. But everything here is reversible. How do I win this? What? Potentially you can remove water from this physically by an azeotropic distillation. How else do I win it? Even if I don't remove water from this reaction will still work. No. Generally, you're going to do something like this at probably something close to the boiling point of the solvent. Notice, what's the likely solvent here, though? Well, methanol is relatively cheap. Why not just use it as a solvent? You're using it as a base as well, and the nucleophile twice. Just use it as a solvent. Okay, so you did that. Why does that mean you're going to win this? Because you've beaten it by numbers. Reversibility is going to require that water that was displaced in this step come back in. If you're using methanol as the solvent, the odds here are several hundred to 1. Water's going to lose, and you're going to win. Not based off of stability, but based off of sheer numbers of the nucleophile required. You have a lot more methanols around than water at any point. Unless you're sloppy again. Alcohols, by definition, hydrogen bond very well, which means by definition, out of the bottle, they're wet. So if you're going to do this, you probably want to dry that first, rather than having, in the case of pure ethanol, at least 5% water by volume. I don't know what it is for methanol. So you probably don't want that around if you can help it. Now, why do we care? Stereochemistry undefined. Look familiar? Seen that functional group somewhere before? That's a hemiacetal. What's the structure? Ribose. In ribose, instead of doing a second alcohol displacement to make the acetal, it gets done with an amine to make an aminal. Like that. We link those together, we call it ribonucleic acid, RNA. Mildly important. Just a little trace. Carbohydrates are not my field, but basically all of the sugars that exist in a cyclic form, monomeric sugars, exist in a hemiacetal format. Cyclic glucose is the same way. This is cyclic ribose. We'll talk about why they take up the exact form they do later on in the course. It has to do with structure and strain, but the idea is there are carbonyls there, and given the chance to close down, they will. Very uncommon that we use alkyl groups separately as an acetal. Much more common is to use a cyclic version. And that is to use ethylene glycol. And we form a cyclic acetal. Like so. The reason that's useful is it tends to be a little more stable. Remember our discussion on protecting groups, they have to survive the conditions of use. The alkyl version, 2 methanol groups coming in to make a dimethyl acetal, not particularly great stability-wise. They don't tend to tolerate even mild acid before that acetal comes back off. The cyclic version, you have to beat on it a bit to get that off. It survives a lot more in the way of conditions, so it's a lot more common in usage as a protecting group. Same basic idea. You can remove that with acid and water and heat. It's not so simple to get it off, but it is reversible. All right, so we have a couple of variations on a theme that occasionally come in useful. One is this. It's occasionally useful to do a sulfur version. Occasionally useful to draw it right. This is a dithioacetal. Generally, the reason you use this is because you want to do something along the lines of what we did in aromatic chemistry, which was to get rid of the carbonyl group entirely. This, under conditions of activated nickel, gets replaced with 2 hydrogens. Next to an aromatic ring, we could do that really easily. If we don't have an aromatic ring present, that hydrogen and palladium reaction from the aromatic chapter doesn't work. You're not taking out a ketone unless it has an aromatic ring next to it with hydrogen and palladium. It's more difficult to get rid of. Why would I want to do that? Like I said, we can use it to build up next door and then make it go away if we want. Should you have to do this, I recommend, I don't know, cauterizing your nose because it's one of the most foul-smelling things on earth. What I'm getting at is this, is if I have this, it doesn't matter what it is, if I take this and I reduce it, I can get rid of that carbonyl. If I do that with something open-chained, Under the same circumstances, it does not react. So getting rid of a carbonyl that doesn't have the benefits of a next door aromatic ring, not so simple. So that's why the thioacetal is useful, because it doesn't matter what's next door to it anymore. It's exploiting the sulfur, not the next door neighboring aromatic ring that stabilizes every type of intermediate. So it's not ideal, but if you need to get rid of an oxygen, it'll work for an aldehyde or ketone. It doesn't work for esters, but it does work for aldehydes and ketones.